figured it out. So if we are looking at this textbook, I think you guys can see the textbook image that I'm looking at on my screen in the sort of recording of this audio. I just wanted to be able to go through with you guys Chapter 5, Section 1. You had made your self-made guided notes on this section, so you already know about it. We are going to be looking at Section 2 going forwards, and I can talk about that in a little bit. But I wanted to just steal your ear, have you listen to me talk. I think I only have 15 minutes on this recording, so I will try and be brief, but to go through our vocab terms and our objectives. So real quick, our key terms are vocab terms here, octet rule. The reason why it's called this octet rule, we're looking for 8 valence electrons. Now, you will likely have more than 8 total electrons, but it is the valence electrons that participate in chemical reactions and forming bonds and moving around to form ions. So with the octet rule, the number 8 is coming from our s and our p orbitals. Your s orbitals, remember, can house 2 electrons. Your p orbitals have 3 rotations. Each rotation can house 2. We remember our p orbitals can house 6 electrons. So that 2 and 6 coming together to be 8, those are our 8 valence electrons, the possibility of having 8 in our outer energy level for main group elements. It is true that we are kind of throwing our transition metals over to the wayside for now. They're not predictable. They're not main group elements. They can form ions. It's just not something that we are going to be predicting in these next sections. We will come back to them when we start talking about nomenclature, though. So when we are looking at the octet rule, the reason why it's important is every atom out there, pretty much, is wanting to have a complete octet, wanting to have a completed energy level. The one caveat for this might be hydrogen. Hydrogen has 1 valence electron in its completed energy level. That would just be energy level 1. It only needs 2 electrons. That is because at the first energy level, there is no p orbital. So we will talk about how hydrogen has a kind of like duet rule instead of an octet rule. But just a little heads up, almost everything else is always going to obey this octet rule. That is also why our noble gases have those properties of being so stable. They already have a complete octet. They have 8 electrons in their valence shell. So if we're talking about all of the other elements, our alkali metals, our alkali earth metals, our halogens, other predictable main group elements, we can make sure that they are going to form ions. Now, we're going to say, depending on how many valence electrons they have, whether they're going to form cations, which are positively cute, or anions, which are, I said, anion sounds like onion. Cutting onions is something that makes you cry, so it's a negative emotion. That is my memory technique. So when we are thinking about ion, again, it's this umbrella term versus a cation and an anion. That is thinking about something that is specifically positive or specifically negative. So I'm just going to scroll down here to be able to show you guys what I mean about predicting these. You can definitely use your electron configurations. So on this page, we see a couple noble gas electron configurations. Just a reminder, those are shorthand electron configurations. So we see our core noble gas and then the leftovers. So 2 valence electrons for magnesium. In this phosphorus example, we have 5 valence electrons in that it has its highest electrons in the 3rd energy level. Some are in the S, 2 of them, and 3 are in the P. So if we look down here, this image that is given in your textbook, and there's kind of a point out to where it is. So it says group 1, group 2, and then it says 13 through 18. So what this is looking at is looking at your S block and your P block. So what they've done is they've cut out the transition metals. If you count these, you will notice that there is 8 of them. So this is, and maybe there's a better, I actually feel like there is not a better periodic table in this particular section, and it will take me a while to scroll through to a better one. But this means that if you're looking at any periodic table, if you're just looking at your main group elements, you can count the columns and say, hey, if it's in the first column, like all of my alkali metals, all of them will always have 1 valence electron. So they will always do the same thing. They will all lose 1 electron to become a +1 cation versus our halogens, which are in group 17 or group 7 of our main group elements, have 7 valence electrons. So they're always going to gain 1, which means they're always going to have a -1 charge. Then we can look at our noble gases and say, well, noble gases already have 8 valence electrons. That is why they don't form ions. They don't react. And again, that's kind of the goal of all of our elements. Hopefully I don't personify these atoms too much, but if it helps you remember the actions that they do, it works. It's good. So moving right along here, the vocab terms, we kind of discussed them: octet rule, ion, cation, anion. I also wanted to talk briefly about our objectives here. So to look at our objectives, the first objective here is relate the electron configuration of an atom to its chemical reactivity. So just a reminder here, let's see, on this page, hopefully that's being projected to you, calcium's electron configuration is given. So you can see how it follows the Aufbau principle and the energy level diagram that was on the back door in my classroom. So with this energy level diagram, again, we're listing all of the total electrons from lowest to highest energy level. It's just the highest energy level electrons we are considering our valence electrons. So that's how we would be able to determine it. We can write out the full electron configuration, say what is the highest energy level. Again, those full, large numerical values, 1, 2, 3, 4, 5, 6, 7, versus those sp, d, and f refer to our orbital types, and the superscript above describes how many electrons are in each orbital. So if we say, oh, I'm at the highest energy level of 4 for calcium, and we have this s2, that means it has 2 valence electrons. They are located in its s orbital. Or the quickie method, which I was just describing earlier, where if we know that our main group elements have 8 columns, and we're looking at any element within those 8 columns, you can just say, well, which column is it in? Alkali metals are the first column. They have 1 valence electron. Halogens are the 7th column. They have 7 valence electrons. Noble gases are the 8th column. They have 8 valence electrons. So again, that quickie method is still based on our electron configuration. It's just a coincidence. It happens to be a little bit easier to do it that way. Our next objective, determine an atom's number of valence electrons and use the octet rule to predict what stable ion will likely form. So when we are talking about predicting which ion is going to form, we are asking, how is the easiest way to get to that complete octet? So in this periodic table, we have some transition metals. That's not what I want to talk about. Parent atoms. I'll get to that in just a minute. I don't know if they have any great images on this textbook here. Hold on, let me get a better image. So just briefly, I pulled over to a PowerPoint slide that I use for my honors kids. This image, you guys will see this. You're just going to get it in a little bit when we start doing nomenclature, but this is reminding us about the set charges that we're going to have for our main group elements. So what we're looking at in this image is a periodic table. We have our elements listed here. We have our alkali metals, our alkali earth metals, we have our noble gases, our halogens. Everything else that is purple is a transition metal. We don't have our lanthanide and actinide series down at the bottom, or these metalloids, these metals underneath our staircase that kind of have these not official terms, the same way, like, our halogens have a specific term, but our oxygen, sulfur, these -2 ions, they don't have a particular name. We just call them non-metals, the things that are above this staircase. And then, so the things underneath are metals. They are main group elements, but we're not going to be worried about them, just the stuff that we see on this image. But real quick, what we're looking at here is the set charges. So all alkali metals have 1 valence electron, so they're all going to do the same thing. We could write out each electron configuration or each noble gas electron configuration and note that they all end in S1 despite being at different energy levels. So having 1 valence electron, we're saying, how do you get to an octet? Do you lose 1 valence electron and have a completed energy level underneath? Or do you gain 7 electrons and complete the energy level that you're in? I like to say that, the universe is lazy, and so everything does the easiest thing possible. The truth behind this is whatever requires the less energy, right? So if something requires less energy, it's going to be easier to do. It's going to happen first. So That's what's happening with our alkali metals. It is easier. We can also think about this in relationship to our ionization energy trend. Alkali metals have a really, really low ionization energy. They're going to lose one electron, versus the opposite is true for halogens. They have a really high ionization energy. In fact, they're not going to lose one electron. They're going to gain one, which is why they have a set -1 charge for those 7 valence electron halogens. If they gain one, they will have 8, and they will have one more electron than the total number of protons, which means overall the charge is a -1. We can see this trend continue, for example, with oxygen and nitrogen being -2 and -3 charges. Oxygen has, we can count its columns, 1, 2, 3, 4, 5, 6. Sixth column, 6 valence electrons. It's 2 away from a complete octet. What's easier? Doing something 6 times or doing something twice? It's so much easier to do something twice. Oxygen is going to gain 2 electrons. Gaining 2 electrons means it has 2 more negative particles, so it has a -2 ion charge. Same thing with nitrogen, but it's just 3 away, so it's gaining 3 electrons. There's a couple on here, aluminum, zinc, and silver, that we will eventually be memorizing that have set charge. But again, we're going to do that when we get to nomenclature, which isn't for a little bit. All right. So the last thing that I wanted to briefly talk about, that last objective about being able to explain why properties of ions differ from their parent atoms, I wanted to remind you guys again that protons identify the element. Our neutrons stabilize the element. They have a big application to the mass of an element. When we talk about isotopes, they're really important, but neutrons not particularly important as far as chemical reactivity that we're discussing right now. So the electrons, it's all about the electrons. So although a chlorine atom is still chlorine, whether it's an atom or an ion form, it's still chlorine, it will have completely different properties. So when we take a look, for example, table salt, that's a good example, and we'll talk about salts real soon. Sodium and chlorine. Sodium is an alkali metal. In its atomic form, and we got this in our jigsaw notes, super reactive. If it reacts with water, it sparks, it explodes. Chlorine, maybe you've heard about chlorine gas being poisonous. The elemental version of chlorine is super, super hazardous. But if you mix sodium and chlorine together, it is a violent reaction. It produces a lot of heat and light. But when you react them together, you get table salt, sodium chloride, which we eat every day. I put it on my potatoes. It's delicious. So what we don't have to worry about is the danger of sodium and chlorine when we're ingesting salt. Now, the reason why this is, they are as ions. They are as Na plus and Cl minus. So they are just as stable as a noble gas. Sodium isn't going to react with the water in my mouth and explode. Chlorine isn't going to poison me when I ingest it. So when we think about ions versus their parent atoms, although the atom itself, we would still call it like the chlorine atom versus the chloride ion, they're completely different. And again, the ions that form, stable, we can predict what they're going to be. And these ions will be things that we'll be able to hopefully see when we come back to class. I think I recorded what I needed to record for you guys today. Sorry if the audio is a little choppy. My pausing and my playing and trying to get a perfect audio is not perfect today. I'll try and make it better. What else was I going to say? I think going forwards, I will try and use this audio equipment as well as like the projected on my screen. Maybe we can do guided notes. I have our next section, section 2, as a guided notes section. Maybe we can do it this way so it's a little easier. Other than that, after we kind of get through section 2, whether it's on your own or you guys are listening to me doing this online thing, I do have a mini poster that I'm going to have you guys do. So I'll give you plenty of time to do it, but it might be a nice little art activity that you're able to do at home. So some